You can unmute yourselves. If you have questions, just go ahead. All right. So let's go. Let's see if I can finish all the stuff to start with integration sometime already on Friday. Okay, so we'll slowly start setting up for talking about integration, and in particular, we're going to integrate around curves. Okay? And so, so we're going to talk about curves in the complex plane, right? So we're going to go back. When you're doing everything else that we were doing, you should really keep in mind, right? We want to motivate things to do things over the complex plane, but a lot of what we did, right, or the way we formulated things could have been over any metric space, even part of it over any topological space, even without a metric. But really, now I want to go. You should think back to the complex numbers, right? This is sort of where I want to. Oh, sorry, I think it's okay. Okay, right, so we're back in the complex plane. And so we're going to talk about curves in the complex plane, right? Think, I take a curve like this, maybe, right? Starts at a point, ends in another, and I think a curve gamma, right? And so I think of an arc gamma in the plane, right? And we want to be able to talk a bit about curves and arcs and so on, right? So this is, again, we have to set up all the language before, because at the end of the day, what we want to say is to say things like, we're going to integrate a function over the complex numbers on an arc, right? And it turns out that this will be an extremely, powerful and useful thing to do. And so we have to, come up with, spend some time just setting up all the language of curves and arcs and so on, right? And the way you can think of this is, right, they can be parameterized by some x, y, right? There's some x of t and y of t, right, for some t in some interval, right? And here I'm thinking of, right, is this being the x-axis or the reals, and this being the y-axis, right? And you can also think, of course, as just in the complex plane, just some curve z of t, right, which could be just xt plus I yt. Okay. Right. Again, basically, this, this map, this z can be viewed as a mapping, right? And so the curve is just the image. Okay, is the image of a closed interval, or a closed, bounded interval, right? That we know is compact by a continuous function. Right, so that's by a continuous function. This is what we mean by an arc, right? An arc or a path, right? In particular, it's compact, right? Because what we just saw. Okay, so the arc or the path, these, right? Let's call these arcs. They are compact, right? Because we just saw there right? We think of them as an image of through a continuous function. In this case, right? This zt. And of a closed bounded interval, so right, so this is just this means it's compact, right? It's the same as compact, and we know the image of compact sets by continuous functions are also compact. Okay, right, and of course, you can have a change of parameters, right? Again, this is like just doing all the, you can have something like. Right, let's say that I have some function that goes from here to here, like continuous. Okay, then something like z of t, right, for z of, for t between alpha and beta, right, basically is the same arc, or looks the same, right, as taking z of phi, right, say t, or let me call it u maybe, right, for u between alpha prime and beta prime. Okay, and this is what we call a change of variables or change of parameters, right? So when you do integrals, just in calculus, you do these kinds of things all the time, right? So this we just call a change of variables. Okay, this is just coming up with language. Now, of course, one ought to decide what do we want to mean by two paths being the same path or two arcs being the same arc, right? So we could say that this is the same arc or two different arcs, right? Depending how we want to define things. We could say, as long as I have a different parameterization, it's a different arc, right? But so it will make sense to actually talk about a lot of properties that are invariant with respect to reparameterization, right? So we'll make a lot of sense to talk about properties of arcs, right, that are invariant and with respect to reparameterization. Okay, and if we think, say, if we take this function to be monotone, right? So we say like alpha of a prime, alpha prime to be alpha, and phi of beta prime to be beta, and the function to be monotone, right? So like it's always, as you walk from here to here, you're doing exactly the same here, right? And there's many things that are in fact, right, and continuous, of course. There are many things that are invariant, right? Things like the start point, right? The end point, the actual image, the set that is defined, that the arc defines, right? Its length, the angles that it has, and things like this. And this will all be important properties. Okay. Oh, someone asked what is written in blue. All I wrote is that it will be important to look at properties of arcs that are invariant with respect to reparameterization, right? So, yeah, maybe this, I meant here with respect to. That's probably what you couldn't see. So reparameterization, such as the start point, end point, the actual set, the length, and things like this. Okay, so let me just see if I don't forget any. Okay, so a few definitions. Okay, so the arc is differentiable like if this z prime t exists and is continuous. So we only call the arc differentiable if it's also continuous. Moreover, okay, so if for example, a good property to have is that okay, maybe I should stop writing in blue. Sorry, I realized, I don't know if it was because it was small or because the blue, so I'll stop writing in blue. All I said is arc is differentiable if the function z of t is differentiable, if the derivative exists and the derivative is continuous. And another nice thing to have is to make sure that as t is evolving, that you understand the rate at which you're going in the path, right? Because that's sort of what this derivative tells you, right? As you're changing t in your parameterization, you're understanding how z is varying. And so it's particularly nice if this is not 0, right? Because if this is 0, then this is not a very good parameterization, right? Because you're sort of, you can be evolving in t, but actually not making any progress in the arc, right? And so if this happens, arc is called regular. So if this happens, say for all t, right, in the interval, then the arc is regular. Okay. Okay, now another important property is, okay, and all these properties sometimes we call, of course, just like in most areas. We call piecewise differentiable, right? Piecewise differentiable, piecewise regular, and so on. When it satisfies these properties piecewise, right? There's a finite number of places where it doesn't satisfy these properties, and then it satisfies these properties everywhere else, right? And more, a Jordan path, call a Jordan path or arc, if it doesn't intersect itself, if it doesn't self-intersect. Right, so you don't, like, if it doesn't do, say, things like this. Right? Okay. So now, yeah, and sometimes we want to talk about, we want to talk about given an, how should I explain this without, like, in a more intuitive way without having to go through definitions, right? Because we're going to be integrating a lot, right? This is how we're going to actually prove most things in complex analysis starting next week. And so integrals will be defined on paths, right? There's sort of a very nice place to define an integral. So we're going to be studying over and over again objects of this type, integral over some path of f of, say, z, right, dz on this path, something like this, right? We're going to be studying objects of this type all the time, right? And now it makes sense to talk about adding and subtracting paths, because if I have a path like this, maybe let me erase over there and try, okay. I'm now trying to give more intuition and less definitions, and then I'll give some more definitions again. Otherwise, it's a whole 45 minutes of just one definition after the other, which is maybe not the most fun 45 minutes. Right, if I have some path, right, and then another one, say, okay, like 2, say, right? If this one, let's say they have a certain direction, right? I would like to be able to say that the path that goes in one and then goes into the other is like the sum of the other two. Right, and because if I think about the integral, it should be true that the integral over the whole thing is like the integral of one of them plus the integral over the other, right? And so, in particular, it means that I should be able to, given a path, so given, a path, gamma, let's say defined by z of t, right? I should be able to talk about minus gamma or gamma minus 1. It depends a bit on what notation we use. I'll use, I think, this one more, and maybe this one not quite as much. But they might show up in some places, so you should keep it in mind. Right? And this path will simply be, the path in the opposite direction. Right? So if I have a path gamma going like this, right? Minus gamma will simply be the same path going in the same direction, right? Because then if I integrate a function on one way and I come back, it should, if things are to work well, it should be 0. Okay. Okay, so we can talk about minus paths. And now just to maybe spending 5 minutes or 2 minutes just saying a few words. This notion of being able to add paths and subtract paths and so on, it's actually what's the background of something called algebraic topology. Because now, if you have some space, right, and you have paths on this space, you can talk about, adding, subtracting paths and so on, right? So effectively, you're putting an algebra on the paths, right? Some kind of algebraic structure, think some kind of group or something like this, right? And now that you're able to do this, it may be that algebraic properties of this object that you just created tell you something about properties of this space, right? And so it turns out that this is quite fruitful, and we'll see examples of this with the winding numbers in a certain way. And so the algebraic properties of this sort of object that we just created, we haven't quite created very carefully, but I just sort of alluded to, of being able to add and subtract paths, turns out that actually, yeah, there's a lot of information about the space in which these paths live, right? And the space in which these paths travel. And this is the key to algebraic topology, of how you can use algebraic properties of things to tell you something about topology of a space, right? And it sort of comes from here. I mean, there's an important ingredient, of course, which is that there I have to define paths up to certain. I have to be able to move the path and it still be the same path. There's a certain. I have to define things modulo something, and this will be clear when we talk about Cauchy's integral formula. But for now, I just want to leave it at that amount of sort of bird's eye view. Okay. All right. So now, the one nice thing of thinking of paths and arcs this way is if you were to take, say, a circle, right? Let's say I take a circle, right? If I take a circle and I think of, say, right, the circle has all points z, such that z minus the center of a circle is equal to the radius, right? This defines me a circle, right? So all, some circle could be all points z such that this is satisfied. Right, but now I can actually define this another way, right? I can just define, and this actually will be a lot nicer, right? Because now we understand, the exponential, and this thing is a lot better. And I can just define it. I can parameterize actually the circle quite nicely by just taking this. For t, say from 0 to 2 pi. Right, and these are exactly the same curves, right? Here, this is just a set. This is an actual arc, right? In particular, I'm telling you which direction I'm traveling it. Right, so I have, let's see here, right? I have my path, my circle. Here, all this defines as a set, while this one actually tells me a parameterization, tells me I'm going this way, right? Because t is 0 is here, and as t grows, it just goes around, right? It also tells me that, it also can do something else, which is if I allow t to go to 4 pi, it means that I can go loop around twice, right? Which here I would have no notion of how many times I'm looping around the circle, anything like this. But also it tells me it can separate things like c and minus c, right? If I want to now go around the circle the other way, right? Let's say that I want to go around the circle this way, right? Then all I have to do is to define z of t to be equal to c plus e to the minus say it, right? And now r, I forgot the r, of course, right? And now I'm walking the circle the other way. Right? And so, by having parameterizations, first of all, in the case of the circle, actually is just as easy to write. We can tell a lot more about the arc, and when we integrate, this will be important. Oh, someone asked if it should be 1 minus t instead of minus t. So where is, maybe here? So if it's here, I'm now just, t here is going from alpha to beta, and here minus t is going now from minus beta to minus alpha. Right? So if it's from 0 to 1, then yes, it should be from 1 minus t. But in general, for alpha and beta, I should really, if I want this to be defined also from alpha and beta, I need to work out what it should be. Right? I need to do the translation of this to where I want it to go. But here I'm just imagining it having different domains. Right? But I agree. If you have a path from 0 to 1, then this one should be, right? If you want this to be from 0 to 1 as well, you just do 1 minus t. Okay. Okay. But yeah, I mean, maybe I should make this a bit more clear for sure, right? I'm thinking of now t as being inside this interval, right? Where t was inside this one. If you want to parameterize in the same interval, you have to move the intervals. All right, thank you. Okay, so let's see what else I want to make sure I state. Okay, these are, now there's a bit of definitions, but they're rather important. Okay, so a couple of crucial definitions. Just, it's just language, but very important language. Okay, definition. So we say that f defined in, right, we're going to define f in regions inside the complex plane, to the complex plane, right? So defined in an open set, let's say this is open. Okay, for now it's not that important if it's connected. Is analytic in an open set omega if it has a derivative in every point. Okay, so a function is analytic in an open set omega if it has an omega, maybe I should say here in an open set, just to make it even more obvious, an open set omega, if it has a derivative in every point of omega, right? Because omega is an open set, then for every point I can zoom in enough to see a ball there, and I can take the derivative from any limit, any sides, right? So all these Cauchy-Riemann equations, all this stuff will hold and all this. Okay. Another one, so if I have now a set, so a set, right? Not necessarily open. Right, so now I'm going to define analytic for a set that's not necessarily open. Say, right, we say that f is analytic. So again, it's just language. We say that f is analytic in A if f is defined and analytic in an open set omega that contains A. Okay, so in particular, a function is said to be analytic at a point if it's analytic in a neighborhood of that point. Okay, so one thing, sort of a bit of at this point, is maybe a little bit of an elephant in the room, which is these multi-valued functions, right? I mean, maybe that's not a great name to call them because multi-valued functions aren't really functions, but let me just be very... Right, so we saw things like the square root and the logarithm. We could define these functions, but many times it was not completely clear, right? There were many options, right? The logarithm of a number could potentially have many possible answers, and the square root of a number could have two, right? When we think of a square root of a positive number, we always think of the positive square root, but if we think of the square root of I, it's not quite clear which one we should mean, right? And so, if we want to talk about functions that we define that way, then we have to be careful about when we talk about their continuity, if they're analytic and all this, right? And so this needs to be handled with a lot of care. And the best way to get a good feel for it is actually by trying examples, right? So this is a very good thing to do in the exercise classes and the homeworks and so on. Just work out a few examples and see what's going on and getting an intuition about it, right? So this is definitely the kind of thing that's much more heavily done on, say, homework and exercise sessions than really what I can do here, because, right, if I were to list many, many examples, this probably wouldn't be the most useful. But let's just look at one example, right? Let's look at the example f of z equal the square root of z, right? So this has two possibilities. Okay, so when we look at a function, right, especially a power, right, this is just z to the 1/2, it's very useful to think about what happens in the complex plane. Okay, let's say that we take, so the modulus of the number will just go to square root of the modulus. So there's nothing going on that interesting about that. So we can go into the unit circle, right? So let's say that this is the unit circle. right? And if a point, if a point is outside the unit circle, whatever happens to its angle will be the same that happens to the angle here, and whatever happens to its norm will, right? Whatever happens to its angle, you can already see it in the points in the unit circle, right? So what will go on is that, right? So if we have a point, let's see if I can do this properly. Right? Let's say that I take this point, for example, right? Or this point, right? If I take this point, what's the square root of it, right? The square root is the point that if I loop around twice, I get to it, right? So, okay, let me see if I can draw this, right? So let's take this point, then its square root should be this one, right? Because if I take this and then I take this again, then I will get to, right? I will get to the green one, right? So let me write this as a W1 and the green point as, let me get rid of this, as say Z1, right? It says, of course, right, their unit norm, so W1 square is equal to Z1. Okay, but there's another point, of course, right? If I add, basically, if I add pi to my number, then when I take the square, not add pi to the number, if I add pi to the argument of the number, to the angle, then when I take the square, this transforms into the 2 pi and goes away. So this guy over here, right, is also a possibility, right? Let's call it, say, y1, right? y1 is also equal to z1, okay? Right? And now the same thing for this point over here, what do I have? I can go halfway, right? So I can go here, right? The angle is just half of what this angle was, or I can do that plus pi, and I can go to some other point over here. Okay? But now one thing we can do is we can try to pick only one of the options, right? So we can say, well, I'm going to pick the branch. Right, so we call these branches. I'm going to pick the branch that, for which f of z, say the real part of f of z is positive. Okay, so I'm going to try to make my square root be always over here. Right, so always on this side. Right, and so this means that in particular for this point, I cannot pick this one, I pick this one, right? So this would be the real square root. For this one, I pick this one, and so on. Okay, but now what's the problem? The problem is, of course, right? Okay, now let me see if I can be a bit intuitive, and then we'll try to fix the problem and see how to work this out. But as I go, let me see, maybe I'll try to draw now a bigger picture. Okay, sorry for the circle not being so circular, but okay, so this is the positive. Right, so real part positive. Okay, and now I'm going to try and use the same notation. I'm going to try and go with green and orange, right? So I take this one, right? So let me do, okay, let's do maybe say z1, right? And this would be omega 1, right? Now I take z2. What would be omega 2? Omega 2 would be this point in the middle, right? And now I can take, say, z3, and omega 3 would be just a point that has half the angle, right? And so basically what's going on is that, right, I'll try to do it with gestures, right? Handmade animation, right? I'm going at twice the speed with the green chalk as I'm going with the orange chalk. right? And now I'm traveling, and so maybe here I mark, I'm going like this, and maybe here I mark another point, say Z4. So far so good, W4. Okay, and now I go and I get here, right? But now once I get here, so let's call this Z5. What are the possible square roots of this, right? It's this number here, right? Or this number plus pi is this one, right? So these are the two possibilities for W5. Okay. Okay, so it would make sense that, I would keep going, but now I'm getting into the real part of the square root being negative, right? Which I decided was not the branch I wanted to pick. But you might say, oh, whatever. I mean, just go with that branch is fine. Okay, and I go, and if I go like this, right? By the time the green chalk gets back to the point 0, 1, the orange chalk is over here. So this would mean that the square root, like if I was trying to be continuous, it means that the square root of 1 would be -1, which of course is the square root of 1, but it's not the one that I decided to start with. So when I then move the green chalk a bit more, back to Z2, the square root that I would be picking is over here. So it's a different one from this, right? And so if I try to define the square root continuously, I clearly get into an issue, right? Try it. So what's one way to go around this issue? One way to go around this issue is when I'm doing this, and I get here, I would like to be able to jump all the way here so that now I'm doing it always with, right? I'm doing it always with positive real part, right? So if I want to define the square root to be always positive real part, when the green chalk gets here and the orange chalk gets here, I need to make a jump to come all the way here. So this function cannot possibly be continuous everywhere, right? Or at least not in the whole circle. And so one way to resolve this issue is to take away this, right? So if I take away this, okay, so now I take this out of my space. Okay, so now I have, say, the complex numbers minus the real z such that is smaller or equal than 0. Right? When I say that a number is smaller or bigger than 0 or something, I always mean real. Right? If I take f, if I define f in this set, then it's okay, right? Because when I move the green thing over, right, and I go all the way to here, the image of this through the square root will be up here, which is fine, right? And I'm not allowed to jump. If I want to go over here, I have to go all the way on the other end, and then the orange one will be here. Okay, so f of z, the square root of z, can be defined as a continuous function, and we can show it's continuous, right? So f, like f of z, square root z, oh, this is z, sorry, square root of z in this branch, like in this branch, is continuous. I haven't defined it's continuous, but it's not so hard. And it's in fact analytic. So that's also not so hard to see, right? Once you see it's continuous, you can easily take the derivative. Okay, but this is a very, I think this is quite a crucial idea and thing to keep in mind. It's the kind of thing that if I just put definitions on the board, I'm not sure it drives the message home as well, which is that these functions that are naturally multi-valued, the way to study them is to define what we call a branch. So we say, I'm going to just take the square root to be whatever is positive real part. Right? And so if you do that, you can't possibly make it continuous in the whole circle. Because if the green, the z, goes travel all the way, it comes back, and the square root would still be stuck over here. Right? And so you have to make sure that you cut the circle somewhere and define it not over the whole complex plane, but over some other open set, right? In region, right? An open region. Okay? And so to actually prove that it's continuous is quite easy. I mean, I can just do it rather quickly. right? And if you now do, say, the logarithm, the cosine, and so on, you can do an exercise of this type for any of these functions. Okay. But I hope this drawing helps. You can probably online you can probably find videos of drawings done professionally that are a lot nicer. But hopefully this helps. Okay, and so it's not so easy to prove that this is continuous, right? You take, for example, like let's say take w equals square root of z. Oh, I keep writing 5 square root of z, and right. So now take say w1. Okay, we're going to take w1, w2, and z1, z2. You're going to need this point, so let's leave it here for now, right? And so. Okay, so of course we have w square is equal to z, right? And now take z1 minus z2, right? 2 points. Okay, this is equal to w, right? w1 square minus w2 square, so this is the same as w1 minus w2 times w1 plus w2. Okay, and so, right, but because these have, so you have that, right? So this is equal to w1 minus w2, but right? So these ones, they both have positive real part. Right? Either of them, right? Because that's the branch we defined, right? And so this is in particular bigger or equal than the real parts of this. So let's say, but they're positive, so the absolute value doesn't even matter. And so in particular, okay, we can say this, for example, where in particular is bigger than with u1 because they're both negative, and so u2 is right, and so u2 is not is bigger or equal than 0, so we can even do this, and so w1 minus w2. Right, is smaller or equal than z1 and z2 over u1. Right, so if the z's are closed, then so are the w's. Right, which is basically what you need for continuity, and you can do the right, and you can do the same thing with to prove now the derivative is quite easy. You just use basically the chain rule, right, or the derivative of the inverse. And you take, it's very easy to differentiate the square, and this will give you what the derivative of the square root is. Right? Okay, so I have 1 minute, which means, unfortunately, I will not be able to tell you what I wanted to finish what I wanted to finish. But let me just tell you in the last minute that now, so this gives us, okay, so we talked about arcs and regions, and we defined topology. Now we talked about what it is for a function to be continuous or analytic in a region, in a set, right? Now that we have this, we can start saying things that are, become quite useful. Like if I have a function who's continuous, who's analytic in a region, and whose derivative is 0 everywhere in that region, then it must be constant, right? So you can now say things like that, and they become actually quite easy to show. Right, so let's say, and then I just want to talk a little bit about conformal geometry on Friday, and yeah, I don't know if we'll start integration on Friday, but definitely on Tuesday. Right, but now you can say already things like, right, say f this to the complex numbers, where this is a region, right, so open and connected. Right, if f is analytic and f prime of z is equal to 0 for all z inside omega, then f is constant. Okay, so how do we prove something like this? Right, I'll just give you the proof in a line. Well, we know that if a region is connected, it can be linked by polygon lines, right? We proved this last time. So now all you have to do is to take 2 points in the region. You want to show that they have the same value. Now draw a polygon line between them, right? Which you can do inside the set. And now look, in each one of these lines, the function needs to be constant, right? Because it becomes just a function over the reals, becomes just functions over the reals. And we know that a function over the reals in the real line, if it's continuous and differentiable, derivative is 0, then it needs to be constant, right? And so this function needs to be constant along all the polygon lines, and so it's constant everywhere, right? So this is basically how we show it. And other things you can say is actually, even if just the modulus is constant, then the function needs to be constant. Or if the argument is constant, or the real part, or things like this. And I'll do this quickly in the beginning on Friday. Okay, thanks so much. I'll be around for a bit longer.